A apresentação começa agora, né?
Yes.
Okay, so good morning, everybody. Welcome to another session of today, March 23rd, we are going to have a presentation by Professor Daniel Canada, and he's going to talk about stability and instability and for submitting and accepting the presentation, and wish everybody a nice talk. Please turn off your microphones and cameras to make the internet connection better.
So first of all, I just want to make sure that my microphone is on. Can everybody hear me and see the screen that I've got here?
Yes, perfect.
Okay, excellent. Okay. So of course, the symposium that is under construction here is in honor of Hildeberto Cabral, and I'd like to just add my voice to the chorus of people who have expressed appreciation to Hildeberto, not only for his contributions in celestial mechanics and classical mechanics, but also for the inspiration, which I think he is uniquely able to mathematicians, students, colleagues from around the world. I really want to again thank Hildeberto for his invitation this century in the late 1990s, I guess, and during the first period of time in the current century. It was a great honor for me to be able to come and talk, and also to learn from the people from the great mathematical community in Recife. So I really want to thank Hildeberto again for that honor. So the
screen.
Oh, really? I thought my screen was shared. I'm sorry.
Yeah, could you? Yes, thank you.
Oh, no. Is it? Hang on. Let me see what's happened here. I had it shared, but now. Oh. Okay. Let me see. It indicates to me that it's being shared. Is it not appearing there?
No,
is this appearing?
I can't see it. I cannot.
You cannot see it? Okay, wait. No. Let me try again.
I guess nobody can.
Well, let me see. I'll try again. Sorry.
Okay. You know, downstairs near to the microphone and the camera, you have an icon to share your screen or a window or.
Yeah. Is that appearing now?
No.
No. Wow.
No.
Okay, what's happened here? Just a minute. Let me see here. Oh, wait a minute.
If you want, you can turn on your camera. There is no problem.
Yep, I think I needed the camera on. Let me see here. Share webcam. Okay, now just a second here. Now let me see. It says, but for some reason I don't.
We can see you now.
You can see. That's an important additional piece.
Yeah.
So let me see there. I'm going to close the presentation, then I'll start it again. Let me just see if this helps.
Yeah, it's a good idea.
Okay. Still, no, there's. So on that little icon at the bottom, Annette, it says I can either close the presentation or restore it, and I'm not sure why it's not appearing there.
No, it's not. It's the icon near phone, a telephone, and after you have a camera, and the next one is supposed to be to share your screen.
Right, and so that little icon is appearing there, but it's
wait a minute. I'm going to
here it is.
restart here. Maybe
okay,
yeah.
Okay. Yeah,
okay.
That's better now.
Sorry. Okay.
That's okay. That's fine. Now, let's see if this comes up. Okay, is that right? Can you see that?
Perfect.
Yeah. Wow.
Okay.
Got it.
All right. So again, thanks for the for the invitation, especially to Eduardo for acting as the coordinator this morning, and also for Hildeberto. So the talk today on stability and instability by index methods, this is basically a little bit of a survey talk. I'm not going to be proving anything specific, but I'd like to give you a little bit of information, and also just a little bit of the landscape on this particular topic, which has been ongoing for some of references, which I could give you here in case you're interested in any of the topics. You could ask me, and I can send you copies. The first paper in that list by Xiwan Yu, Long, and Sun. I'm not going to be talking about that. I think it's an important paper on the linear stability of elliptic Lagrangian solutions of the planar three-body problem. Just a little bit of reading if you're interested in the topic. You'd like to find out some more. I'd like to just express my appreciation to Henry Kavle, my PhD student, who's working with me on some of these topics. So the introductory comments here, just as follows, right? As I've mentioned, the topic of using index theory to attempt to uncover stability or instability of families of periodic orbits, not only in celestial mechanics, of course, developed into a very active area of research with many people contributing to this area. And the investigations basically fall into two kinds of categories, which are very frequently interrelated. The The first is perhaps best exemplified by the of symplectic continuous curves of symplectic matrices in the symplectic group, and he's looking at the homotopy invariant intersection theory of those curves of Lagrangian subspaces with a Maslov cycle, which is a transversely oriented collection of subspaces generated by a given Lagrangian subspace. I'm not going to be talking about that. This is the sort of the oops, let me get a yeah, this topic is the one basically introduced and developed by Yiming Wang. And the other investigation basically is one which tries to use the variational theory of closed orbits in Hamiltonian systems to gain information directly on the indices and their iterates. Now, the important idea there is that the iterates of these indices is the key to understanding the connection to stability of periodic orbits, which is not really surprising. If you think of a linearized Poincare mapping, for example, for a periodic orbit, of course, it's the iterates of that Poincare mapping which help to determine whether or not a given fixed point or a periodic point is stable or unstable. So let me move then to just a general discussion of the variational aspect and how this can be used in certain settings in order to gain some information about the stability of periodic orbits, right? So let me look at a setting for this discussion. We could look at a Riemannian manifold and a Lagrangian function on the tangent bundle of that manifold. And we're assuming that we have a Legendre condition, which is this one right here. The Legendre condition just says that the fiber derivative in the velocity direction of the Lagrangian is a positive definite quadratic form. And then, so starting with that basic bit of information, the action functional then is defined on a Sobolev space of curves. So here's the action function. We integrate the Lagrangian over the period capital T that we're looking for. And the Sobolev space is the function space of absolutely continuous curves with whose derivatives are L2 functions. And we put periodic boundary conditions in here. So the periodic boundary conditions require essentially that x of 0 is equal to x of t. X of 0 is equal to x of t. Okay, and of course the critical points of the action functional correspond to solutions of the Euler-Lagrange equations with periodic boundary conditions. So you get both periodicity in the configuration and in the velocity by using techniques from the calculus of variations, right? So that's the basic background, of course, that we refer to as the variational structure for periodic orbits, and to also work equally with the Hamiltonian, which is a mapping on the cotangent bundle into the real numbers, right? So the Legendre condition gives us the Hamiltonian formulation of the problem in terms of using the symplectic structure and the flow of the Hamiltonian vector field, right? So we have that basically working for us in the background. Now here's the kind of questions I think which are really interesting and which are not fully answered, but In certain settings, there are specific answers to these questions, and I'll try to illustrate that a little. Specify conditions which guarantee that a minimizing critical point of the action functional corresponds to a periodic orbit in the cotangent bundle, which carries local stable and unstable manifolds. That's a very natural question. I mean, it goes back essentially to Poincaré in 1905, who was where he was looking at the closed geodesics on orientable surfaces, and made the observation with the proof that the minimizing geodesics in that setting always were unstable, right? And so then you can ask more generally, is it always true a minimizing critical point corresponds to a periodic orbit which is unstable? And the answer to that is no, it's not. That answer is no. But there are special cases, especially with symmetry invariance built in, equivariant action functionals, in which case you can conclude that that is true. Now the second question is one which is also very tantalizing, and that's, can we specify conditions which guarantee that a mountain pass critical value of the action functional carries an elliptic stable periodic orbit, right? So this is another aspect of this variational theory, and the question I think is very, very interesting, very tantalizing. In certain situations, the answer to that is yes, and I'll show you some of those perhaps in the little later on in the talk. Okay. Let's see here. Let me just continue a little bit with the general structure of this variational problem and how we get to the indices of these periodic orbits. So that comes from the second variation. The second variation is an invariantly defined symmetric bilinear form on the space of periodic variations. And the periodic variations are these ones. These are tangent vector fields along so here X is a critical point. So X is a critical point of the action. And we're looking at the essentially variation vector fields along that and again, we're asking that these variation vector fields belong to a certain function class, the Sobolev space, or actually a Hilbert manifold of vector fields which are absolutely continuous and whose derivatives are in L2 basically. That's the idea there. And again, we're putting for the structure of the problem, we're putting on these periodic boundary conditions for these for the space of variation vector fields along the critical curve X. And then we can now look at what the second variation is, and here's a formulation of that second variation in a fairly general setting. Here again, we're talking about a Lagrangian with the Legendre condition built in, and we can look at the second derivative of the action functional as a bilinear form on pairs of variation vector fields delta x1 and delta x2. And there's the formula for that. And the operators or the matrices P of t, Q of t, and R of t are given as these second derivatives of the Lagrangian along the extremal curve x of t and its velocity x dot. Okay, and in that formulation of the second variation there, I've indicated certain quantities to be transposed, and I'm indicating that transposed by a superstar on the relevant objects. And of course, these quantities P of t and R of t are symmetric operators. This is P of t is a positive definite symmetric operator, and R of t doesn't necessarily have to be positive definite. Okay, so there's a little bit of information on that second variation. And now let's look at the Morse indices connected with the second variation. And before I look at the Morse indices, what I'd like to do is talk about complexifying the space of variations along the periodic orbit, complexify that space and extend the self-adjoint operator A, which is the second variation, to the space of complex valued variations. And now we're putting in slightly different boundary conditions on that space of complex valued variations using the same function space setting. But now we're asking that the variation vector fields satisfy delta x of 0 is equal to omega delta x of t, where omega is a complex number in the unit circle of the complex plane. Okay, and the omega Morse index of the second variation then, which will be denoted by this particular item here. That's the index we're looking for. It's the maximal dimension of the complex vector space V, where V is a subspace of the function space of complexified tangent variations. And we want the second variation to be strictly negative on that subspace V. And again, we put in the boundary conditions on that subspace. So we denote the Morse index, that is the number of negative eigenvalues essentially counted with multiplicity of the second variation, restricted to that subspace. And we indicate the boundary conditions with the superscript omega on the index, and the interval on which we're discussing the index by the lower subscript capital T. Okay, so we're talking about the number of negative eigenvalues essentially of this self-adjoint operator, and we will now look at what you can do with these omega Morse indices. And the basic interest in the omega Morse indices relates to an iteration formula for the Morse index with periodic variations. And this goes back to Bott in about 1956, and which was updated and brought to life again by Yiming Long in about 1999. And here the idea is that we can recover the Morse index over multiple periods, right? So this is the iteration formula that we're talking about, iterating the index from 1 period to 2 periods, 3 periods, etc. Right? So the Morse index over the interval, multiple of the period, little k times t, k is a positive integer, is the sum of the omega Morse indices, Morse indices, where omega is a kth root of unity, right? So that's the basic idea. If we sum up these omega Morse indices over the kth roots of unity on the unit circle, we can recover the Morse index over multiple iterates of the basic period 0 to capital T. And we denote that calculation by this one right here. The +1 refers to the periodic boundary conditions. So again, what we're looking at is delta x of 0 is equal to delta x at kt, right? So we're looking at periodic boundary conditions, but now over multiples of the fundamental period, capital T. And so the +1 refers to the fact that those are the boundary conditions, and the interval in which we're talking about is indicated by the lower case subscript kt. So in particular, for the double cover of a critical curve, so the double cover just means we're now looking at a periodic orbit over the interval from 0 to capital 2t, right? This is still a critical point of the action function on that time interval. And the Morse index of the second variation over that time interval is just the sum of two omega Morse indices. Omega is equal to plus or minus 1, right? So this one here is the standard Morse index with periodic boundary conditions. This one here is the Morse index with anti-periodic boundary conditions, right? So the Morse index over the double cover is just equal to the sum of the indices, one for periodic boundary conditions and one for anti-periodic boundary conditions. Okay. All right, now let's see here. So we can use that in the following way. On the other hand, if we start with a low dimensional, or if we restrict ourselves to a low dimensional system, say the dimension of the configuration space script x is 2, then here's some additional information about elliptic stability in that particular setting. And here we're talking about the flow of the capital or little phi of the Hamiltonian vector field. So we're looking at the flow of the linearized flow of the vector field evaluated at the period, right? Which is just essentially the monodromy matrix of the periodic orbit after time capital T. So that monodromy matrix is elliptic stable if and only if the sum of these two Morse indices is odd, right? And I can explain that a little bit, just sort of intuitively why that's true, or how that comes out to be true. So if we look at in the complex plane of the unit circle again, here's the unit circle, the complex plane, here's the real line, right? And of course, for the low dimensional setting, we have a single pair of essential eigenvalues for the monodromy matrix, right? Given the fact that it's the Lagrangian is autonomous, that means we're going to have a pair of non-essential eigenvalues coming from the conservation law of the Hamiltonian and the time independence of the Lagrangian. So that gives us essentially a pair of trivial eigenvalues, and then the non-trivial eigenvalues come in pairs, lambda and 1 over lambda, and those pairs can either be on the real line, right, or on the unit circle, like that, right. Now, when we're looking at these Morse indices, say this one here, the Morse index for periodic boundary conditions, what this is measuring is what this measures is essentially the passages through the value +1 for a continuous curve of symplectic matrices. So in other words, if you start essentially a path of symplectic transformation, such as d phi t, right? Look at this path. It starts at the identity, and the eigenvalues can move on to the real line or move on to the unit circle. If they move on to the unit circle, the Morse index will click by +1, right? That will click the Morse index by +1. And in fact, every further passage through +1 will affect that Morse index I +1 lower t. If the eigenvalues pass through +1, either on the real line or on the unit circle, such as this kind of a pattern, then I +1 of t will jump by 2. And if the eigenvalues transit through +1, moving from either the unit circle to the real line or vice versa, that index will increase by +1. And the same situation occurs for the case of eigenvalues as they transit through -1. So here's +1, here's -1. As they transit through -1, you again get the behavior of the Morse index I -1t connected to the number of or the kind of transit through that eigenvalue -1. If the eigenvalues move from the unit circle onto the real line in this particular pattern, right? So we get this kind of a transition, then the eigenvalue, the index I -1t will increase by +1. Whereas if the two eigenvalues pass through -1 without moving onto the unit, without moving onto the real line, then the eigenvalue I -1 will increase by +2. So what that attempts to explain is this particular formula that I've written up above there, that the linearization or the monodromy matrix at the period point is elliptic stable if and only if the sum of those two eigenvalues is odd. And so if we put that together with what I just mentioned earlier, we get this kind of a statement here for the low dimensional setting, that we get the linearization of the flow at the period point is elliptic stable if and only if the index, the Morse index with periodic boundary conditions over twice the period is equal to 1, is equal to 1 mod 2, an odd number, right? So if the Morse index of the double cover, that's over the time period 2t, is an odd number, we get elliptic stability, and if it's an even number, we get instability based on that observation. Okay, now there's different kinds of applications of this to different settings. I'm going to talk about one which is kind of unexpected in a way, which is instead of a continuous dynamical system, I want to talk about a discrete conservative dynamical system. And a very nice example of this, of course, is the billiard ball problem. And so this is the description of a motion of a mass point in a convex domain in the plane with elastic reflection at the boundary. This system has been studied extensively over the last 100 years, starting, I think, with Birkhoff in about 1927. And the idea there is, if we look at a convex region in the plane and the boundary of that convex region, call that gamma. So I'm taking this this notation directly out of Ken Meyer's first edition of his book, so I'll use that notation. And elastic reflections at the boundary just means that the angle of incidence and the angle of reflection are the same. So we have a picture like this. Maybe we parameterize the boundary by, say, arc length, S belonging to the interval 0 to capital L, mod the length L, arc length L. And so then we get elastic reflections at the boundary. So we get something like this, and then something like that. Okay, so it's coming in, moving along there, and coming out like that. And you can coordinatize the contact points on the boundary of the billiard ball, right? By, for example, using arc length S along the boundary. Maybe call this one S primed, right? The next point of contact, and then the angle of reflection is this one here, say alpha, and this is the angle of the next point, alpha primed, like that. Okay, and we'll denote the length of this segment L of S and S prime, the Euclidean length of that segment by L of S and S prime. And then there's some very simple and nice relationships. You can see what the differential of L is. The differential of L looks like this. It looks like cosine of alpha ds, and then minus cosine of alpha primed ds prime, like that. So the differential of the Euclidean length of that segment can be calculated in this particular way. So these angles are the same, of course. Like that. Okay. So there's the basic idea, and we can coordinatize this the bounces with the successive bounces by these parameters I'm indicating, alpha prime, the alpha and alpha prime, the angles of incidence and reflection, and the particular points denoted by arc length along the boundary. Okay. Now, this gives a billiard mapping on an annulus in the plane, and the annulus, of course, is just the annulus is equal to gamma across the interval 0 pi. Okay, and it's a simple calculation to show that you have an invariant two form, which is sine of alpha d alpha wedge ds. This is invariant under the billiard mapping, and then if we change the coordinates essentially to s and cosine of alpha, then we get an area preserving mapping of this annulus, right? And now the annulus looks like this. And here's a little simulation of what a billiard trajectory might look like. You can see the complexity of a general boundary and a general initial condition. What's the initial condition? Here it is, right here. There's the initial condition. That we can follow this this billiard trajectory over many successive bounces off the boundary, and we're interested in the structure of these bounces. In particular, we're interested in the structure of periodic billiard trajectories. That those are billiard trajectories which will close up after a certain number, say capital N of bounces, right? This one looks like it's almost periodic. There's another little bounce here, up there, which looks like it's very close to an earlier bounce, but I wouldn't speculate on whether or not this is a closed trajectory or not. Now there's a very natural way to generate n-periodic orbits of the billiard problem, and that's by using a variational structure. So we have this area preserving mapping of the annulus. That's the symplectic nature of the mapping problem we're talking about, and we can now look at basically the variational structure, which correspond to sequences on the boundary, and I'll change the notation from S to X now. So we look at n-periodic billiard trajectory, which correspond to periodic sequences. Those periodic sequences have to extremize this function, where we use the Euclidean length L between successive bounces, and we sum up the lengths, those Euclidean lengths from I equals 1 to n, and we impose the boundary condition, the periodic boundary condition on that functional to gain a periodicity of the underlying trajectory. Now, the fact that these Billiard trajectories correspond to extremal sequences of this function is a fairly easy exercise. You can see what the condition for an extremal would amount to, right? And then you can use exactly the calculation I mentioned earlier, that if you look at dl, which is equal to d1l times dx1 plus dql by dx2. And this is exactly this. So the condition for extremality is that this is equal to 0, right? And instead of 1s and 2s, we could put I and I plus 1. And that condition is exactly the same as the earlier condition, which allowed us to generate the symplectic mapping from the Billiard sequences. Okay, so the fact that we have a variational problem here is quite useful. We can use that variational problem to generate critical points with periodic sequences, for example, right? Now, I'm not going to discuss that, but I will discuss I would like to discuss just a little bit the structure of the instability or stability of these periodic sequences. So for an n-periodic sequence, the eigenvalues of the linearization of the mapping B sub n are lambda 1 over lambda because of the area preserving nature, where lambda is either a real excluding 0 or on the unit circle. And of course, what I mean by dB sub n, the linearization of the nth iterate of that symplectic mapping is just the composition of those mappings from starting at x1, y1 and ending at xn, yn. Okay, so we're looking at answering or trying to answer the question: under what circumstances will this linear 2x2 matrix dBn be either stable or unstable, right? When the eigenvalues are on the real line, we get instability. When the eigenvalues are on the unit circle, we get stability. Okay, so here's the theorems that are relevant to this, and this is work that has been completed with my graduate student Henry Kavli. So first of all, looking at the Morse index of this functional over twice the period, right, 2 times n, with periodic boundary conditions, we get the same kind of structure of the splitting of this index in terms of either periodic boundary conditions or essentially anti-periodic boundary conditions. They're not quite the same as they were in the continuous case, but it's completely analogous. And for an n-periodic Billiard trajectory, the one that we're discussing, the linearization of the nth bounce of the underlying symplectic mapping is elliptic stable if and only if the Morse index with periodic boundary conditions over twice the interval, twice the period, is an odd number, mod 1 mod 2. We get the same kind of structure of stability and instability in the Billiard problem. And what I'll just finish up with is excuse me. What I'll just finish up with is some simulations that Henry has done for for elliptic and hyperbolic billiard trajectories. Maybe I'll just say a few words about this because the pictures make more sense if I say this, right? So the pictures will be coming up. I'll come back to these in just a moment. We're looking at these billiard trajectories, and in this case, we're talking about billiard trajectories of period 2, right? So 2 bounces on the boundary, and in order to get stability or instability, we have to double the interval. So we're talking about 4 bounces on the boundary, and we're going to look at some calculations of those indices over that doubled interval. These simulations have to do with the ellipse, right? So we're looking at the boundary of an elliptical domain. This is kind of a thin ellipse where the major axis is bigger than square root of 2. And in this case, the minor axis is always stable for the ellipse. And that's a simple calculation for the period 2 minor axis bounce. That's always stable. And it's interesting to understand how that corresponds with the calculation of the indices, right? So let me just say something about that with the variations of periodic billiard trajectories and how we can attack this particular statement here, right? The negativity of the second variation along certain variations, and the variations, of course, look like this. Their sequences delta x1, delta x2, etc., up through delta x2n plus 1. Again, we're looking at the interval from over double the period. And the periodicity condition just asks us to set delta x2n plus 1 is equal to delta x1. Okay. Now, the contribution to the index of that of the second variation here can come from either Dirichlet boundary conditions. That's this one here. That's where delta x1 is equal to 0, which is also the same as delta x2n plus 1. Or they can come through a contribution due to what we refer to as a Jacobi variation. So delta x in this case, so in these cases, the Dirichlet boundary conditions are not related necessarily to a family of extremal. They're not variations which can be which are derived from a family of extremal sequences, but the Jacobi variations are. So the Jacobi variations are variations through a family of extremals with the periodic boundary condition. Okay, so the family of extremals, we're looking at a parameter E, if you like, and we're differentiating that family with respect to the parameter E, right? And the family of itself, of course, is a sequence of length 2n plus 1, and we're putting on the boundary condition x2n plus 1 is equal to x1 for each element of the family. We're differentiating that family in order to generate this Jacobi variation. But it's important to recognize that I refer to this as a family of extremals, but it's not extremal with respect to periodic boundary conditions. It's only extremal with respect to the generalized negative length functional that we use to describe the variational structure of these things. So we don't, in this case, when we're looking for periodic extremals, of course, we put on the boundary condition, which is essential to gain those, but we could just look at an arbitrary trajectory, which is extremal with respect to that length, but without the boundary conditions built in. Okay, and that's what we're talking about here. And this is so this Jacobi variation essentially has periodic boundary conditions in the configuration, but not in the momenta, right? Not in the momenta in general. And the defect in this sequence is measured as the concavity in this index. So there's 2 contributions to the index, one coming from Dirichlet boundary conditions and one coming from these variations, which I refer to as Jacobi variations. Now, here's the pattern. The Dirichlet boundary conditions give rise to conjugate points of the Billiard trajectories, right? So you can see that in the upper diagram there. What we're looking at is a spray, if you like, a spray of Billiard trajectories which move through the periodic point as we vary a parameter E, and that spray of trajectory, actually, I'm sorry, it's the spray starting at the initial point and varying only the momentum, only the angle of incidence and reflection at that point. And then we follow that family through two bounces and we generate conjugate points. The conjugate points correspond to increases in the Morse index of the second variation. We count those number of conjugate points. We also have to count this concavity term, right, which comes from the contribution due to these these Jacobi variations. And in that particular setting, the Jacobi variations are not the same, of course, as the Dirichlet boundary conditions. In this case, we're using something like Neumann boundary conditions. We look at a family of extremals or Billiard trajectories which start orthogonal to the boundary. Here's the point. Here's the initial condition for the periodic one. So we start with a family of family of Billiard trajectories starting orthogonal to the boundary, right? And in this case, Henry's used the natural symmetry of the ellipse to be able to generate how this family develops over two bounces, and he measures the concavity after four bounces. Concavity is 0 in this particular case, and you add the concavity to the conjugate index. That gives us an odd number, which in this case is just equal to 1. Okay, and then just quickly to finish up, one more example. This is kind of also a stable Billiard trajectory, and this is where the major axis is smaller than square root of 2, and the minor axis still is equal to 1, the length of the minor axis. And in this case, we generate, with the Dirichlet boundary conditions, we're generating two conjugate points, and a concavity is equal to 1. So the sum of those two contributions again gives us what we expect from the theorem, which is that the index of the second variation over double the period is an odd number, in this case equal to 3, right? So actually, in the first case, let me just point this out. In the first case, what we have here is a mountain. So what this picture is basically telling us is that the double cover of the period 2 bouncing periodic trajectory, the double cover of that is a mountain pass, right? And this mountain pass is elliptic, right? In this case, it's not a mountain pass. It's not a mountain pass because the index has increased from 1 to 3, but we maintain that that parity of the indices of the Morse index and in terms of the elliptic stability of that one. And then the last example here is an unstable Billiard trajectory. So if we look at the period 2 bounce along the major axis of the ellipse, we get an unstable orbit. That's always true for every ellipse. But we can do the same kinds of calculation. We start up here with a spray of trajectories or Billiard trajectories, starting from the initial point and with different angles attached to them, different values of the momentum, if you like. And we generate, in this case, three conjugate points on the doubled interval over 4 bounces, together with a concavity term, which will be +1. And you add those numbers together, you get 4 for the Morse index of this particular unstable billiard trajectory over twice the period. Okay, so I'm going to stop there. I'll thank the audience for their attention, and I'm happy to take any questions if you have them.
Okay. Thank you very much. Thank you for the very nice and rich talk. Are there any questions?
Okay, can you hear me?
Yeah, I can hear you.
Yes.
Can't.
Yes.
Yes, I can hear you, Jeff.
Okay. Oh, okay. All right. Dan, so
Yeah.
I'm quite surprised that your theory that if you look at 2t, you
Yeah.
can determine the stability. So as I did quite many years ago with my student Dan, and you were postdoc, and
Right.
the problem for instability is really easy to obtain. For example,
Yeah, that's correct.
For stability that in general,
Yeah.
2 period, it doesn't solve the problem. 3 period, any number of period, finite iterates, that does not give you the stability. The stability, you have to have additional conditions. That's why when we wrote the paper, that we gave a very simple and elegant kind of statement about instability. But for stability, we could state some abstract theorem, which is not easy to verify and which is not exactly kind of it looks abstractly probably nice, but it's not very useful or practical. So in your case, 2-dimensional, of course, that was certainly make life easier.
Yes,
and,
that's the whole issue.
Using two period, you can determine the stability. I mean, any period you have give certain conditions, you can determine instability. Determine stability just by iterate twice. I'm quite surprised.
Yeah, it's well, I mean, it's a little bit surprising. I mean, well, actually, honestly, I think somebody important once said that these discoveries always seem natural after you have a look at them, right? But they're hard to predict. And the fact that in the low dimensional setting, because you only have, this is the basic idea for this step, is that because you have only a single pair of essential eigenvalues to worry about, and those eigenvalues can leave the unit circle only at plus or minus 1, right? Only at plus or minus 1.
Exactly.
Right. And
so that's about 2-dimensionality.
Yeah, that's the low dimensionality there. In the higher dimensional case, of course, you can get you can get Krein collisions at a multiple number of points on the unit circle, and so the complexity of the bifurcations there is much harder. But in the low dimensional case, you can only get the transitions from stability to instability at plus or minus 1, and the Morse indices with either periodic or anti-periodic boundary conditions covers that for you if you are careful about how to measure the increases in those indices as the eigenvalues pass through those 2 points, plus or minus 1. So that is basically my explanation of why that surprising result is true.
Yeah, because I mean, so basically that. Well, my second question is that is it verifiable your formula that the for stability, because often that the condition that to verify is harder actually than directly to verify with the linearization.
Jeff,
so
I didn't
in this
quite.
Case that giving a my second question is, for example, for 2 dimensions, action minimizers is always unstable. And so what I and my former student then did was that it's in 1 dimension, 2 dimension, it's always unstable. Then we proved for 4 dimensions, 6 dimension, any even dimension, you have instability.
Instability.
That's the power of the variation method. Because 2 dimension, you have fancy tools like curve cutting, shortening argument. But in high dimensions, you don't have that. But we are able to show even dimensional space. If it's a action minimizer, it has to be unstable. Then we looked further, try to get something about the stability. But the stability, if you iterate any periodic points, after you have a large enough number of iterates, you can decide, you can determine stability by index. But the number of iterates depend on the periodic points itself. So sometimes probably need 2, sometimes need 4 iterates, 3 or 4 or 5 iterates to get the stability. And so in your case, that's why I'm saying that I'm surprised that you just do 2 iterates. But here in your case, it's hidden in that formula. So you do second iterates, you look at the 2 indices, and then you add up and look at the modulus. And so I suppose that that's hidden there.
Exactly.
The complexity is basically transferred into the complexity of that formula. So do you have, for example, in high dimensions, that any kind of a similar? So if you do 3 iterations and you get nice formula, and
that would be a wonderful
the complexity.
That would be
the complexity into your formula. So that's why.
That would be a wonderful result, Jeff, if it were true. If for higher dimensions you'd use 3 or 4 or 5 iterates. I don't know, and I don't believe that's possible.
Well, you can always write. No, you can always write abstract statement like that. But the question is whether it's verifiable. That is, whether your condition can be easily verified. For example, we know Morse index, then we know stability. That's what we did. We know the Morse index. I can tell you half of the time that you know instability. So the Morse index itself is not sufficient for stability. So
no, it's not.
A large number of iterates.
But I mean that iteration formula with the omega Morse indices, that's a crucial fact, and it allows you to look at the higher iterates, and in particular for the low dimensional case, for the double cover. It's very simple. You're looking only at the indices connected with plus or minus 1, and that simplifies the problem dramatically, at least in the low dimensional case.
Okay, all right. So also, sometimes these things becomes, as I said, it's if you look at the iterates, it becomes not finite dimensional problem. It becomes it's sitting in an infinite dimensional space, like the
correct.
Theory. That so basically the difficulty is coming from there. That's why often that you need something more intrinsic, more complicated. But it's nice that you can in this particular case you can do 2T, and so it would be nice to have for high dimensional space if you have
for higher dimensional space.
So that's one problem.
So for higher dimensional space.
Doing.
So for higher dimensional space, the problem is still obviously wide open. I don't see how to simplify. I think my feeling is that you would have to put some kind of symmetry constraints on the curve, on the functional. So you're using some kind of equivariance to perhaps use some symmetry groups to try to collect the kinds of bifurcations that are possible in the higher dimensional setting. But I don't have any real good answers on that particular aspect right now.
So exactly. So if you have in high dimensions that if you have certain symmetry or your periodic points is symmetric, like that these things Anish and Snare did for these kind of action minimizers with all these symmetries, then you can certainly apply these to the index theory. That certainly simplify a lot of I mean, at least reduce the dimension.
Yeah. Yeah, that's that would be the.
It is. Yeah, it's an interesting kind of interesting topic that on the symmetry group, and you have a periodic point, and what kind of things you can get from the index theory itself. Okay, well, thank you very much. It's a nice talk.
Okay, thank you. Now, who else has got any questions? I have a lecture I have to give in a few minutes here, so I'll have to go.
Okay, let's be quick here. Jai Coiler is asking for references on the work of Billiards.
Yeah, Jair, if you could just hold off on that. My student Henry is writing this up frantically, even as we're as we're speaking here. So he's working on that. The interest in the billiards, I think, is quite surprising, because I couldn't find any reference at all to statements of stability or instability. Sorry, in particular references to questions about stability of periodic billiards. So I think it's an interesting and surprising application of those general ideas I gave at the beginning. But I'm happy to get him to supply some references for you as quickly as possible. Okay.
Okay. Do you hear me? I would like to add a challenge for both of you, Harry and you. The most outstanding problem in planar billiards right now is to prove the conjecture of Birkhoff that the only integrable planar elliptical billiard is the ellipse.
Yeah, that's a good one.
And I was impressed by the calculation in the example you gave.
Yep.
And I wonder, because if you add to the general theory, probably you have already done it, what extra conditions one gets when you impose, say, integrability.
Well, that's a good question. Yeah,
perhaps, but it's just a perhaps.
Yeah.
You get an extra tool, because there have been lots of work recently and some advances in particular cases, for instance, discrete symmetries that prove this conjecture. So I wonder that, with the help of your tools, one could get a complete proof.
Well, I guess that, just sort of thinking quickly, if you have an integral problem, presumably the entire phase space is foliated by invariant curves, right? And those invariant curves, I suppose, correspond to caustic curves in the interior of the billiard region. Now, we didn't look at what that would imply if you have a periodic orbit, which is bouncing in such a way as to intersect the caustic curve inside the boundary of the billiard. We haven't looked at that at all, but that's a natural question to investigate. Are those ones always elliptic stable or not? I don't know. I don't know the answer to that. Probably not. I mean, probably they're not, but it may shed some kind of light on the general problem you're discussing there.
Okay, I look forward to see your papers
Yep.
and this, who knows, this extra bonus.
Extra condition, yeah. Though that's a good condition to put on there. And does it help to answer that conjecture of Birkhoff? I'm not sure.
Thank you.
Okay, you're quite welcome.
Then do you have a few more minutes for
Yep,
questions?
I've got a couple minutes here. Yeah.
Okay, Maísa, maybe you want to ask your question?
Yeah.
Maísa?
Hello.
Hi, Maísa.
Hello. I would like to know if you applied, you computed these indexes for the equilibrium of a restricted body problem, L4, L5.
That's something that I think is in the near future. We haven't done that yet, but it's something that I would like to look at very carefully, especially with regard to the recent talk of Ken Meyer, where he discussed the Hamilton-Hopf bifurcation at L4 and L5. So I haven't looked at these index calculations at those relative equilibria, but that's something I'd love to be able to do. I haven't done that yet.
Oh, great! Thank you.
Okay, thanks, Marisa, for the question. Also, Joaquin Delgado has a question.
Yeah, Joaquin, go ahead.
My question is that can it be extended to the T-periodic?
Yeah, yes, it can. It certainly can. And in fact, the question about the low dimensionality, that's where I first looked at this issue of the indices in the case of 1.5 degrees of freedom. Okay. So that this discussion can certainly be extended to non-autonomous Lagrangians, T-periodic Lagrangians. Absolutely correct.
Just one more stupid question. It looks very much to the theory of the Hills equation. I mean, if you consider the Hills equation as a variational problem, it seems that you can recover all theory of Hills equation. Is that right?
I don't know. That's another good question, Joaquin, which I don't really have an answer to. If I had another lifetime in front of me, I might be able to answer that question.
Nice stuff. Thank you for that.
Okay, you're welcome. Okay.
Thanks, Joaquin. I heard someone, Hildeberto.
Yeah. Hi, Dan.
Hi, Hildeberto.
Do you have any information about the iteration formula? If they in more than 2 degrees of freedom, if
no,
the iteration comes from a...
Yeah, I wish I did, and there as I was explaining to Jeff, I think that a natural way to try to attack that problem might be to have a certain symmetry group attached to the periodic orbit. So you're looking at some equivariant action functional, and you look at the iterates of the indices under that kind of equivariant assumption. That's something which is sort of, again, I've left for the future. I haven't considered that very carefully yet. But I mean, it's a tantalizing question. Does this kind of statement of stability in low dimensions, does it carry over in higher dimensions? There's some kind of symmetry rigidity which helps you to make those arguments. I don't know the answer to that, but my feeling is that there should be something there.